Good morning, everyone. It's 11:05, so I hope you are ready to continue today's session. And I'm very happy that for today's open lecture, we have an esteemed guest, Professor Aljoša Smolic. Very happy that you're here to enlighten us about AI-based volumetric content creation for immersive experiences and production workflows. But before you start, let me tell the audience about you. So, Professor Aljoša Smolic has an extensive career in researching and developing immersive technologies and experiences. Currently, he is professor in the computer science department of Hochschule Lucerne in Switzerland, as well as co-head of the Immersive Realities Research Lab. Before that, he was a research professor of creative technologies at Trinity College in Dublin, where he was heading the research group VSense. And before that, he was at Disney Research Zurich as a senior research scientist, as well as head of the Advanced Video Technology Group. He also had a period at Fraunhofer Heinrich Hertz Institute in Berlin, where he was heading a research group as scientific project manager. Professor Smolic has received his PhD from Aachen University of Technology and was a lecturer at the Technical University of Berlin and ETH Zurich. His research interests include immersive technologies such as AR, VR, volumetric video, 360 omnidirectional video, light fields, virtual effects, and animation, with a special focus on deep learning in visual computing. I think you will find his talk truly inspiring and amazing. And I hope also that after his talk, we have a lively discussion. He's here to answer all the questions you might have. Welcome. And please take the stage.
Hello, hello. Test, test. Sounds good. So I assume you have heard what I said so far, so I won't repeat that. But no, it's really a pleasure to talk about something that I've been doing since over 20 years, basically, which is volumetric content creation. So capturing the real world and turning it by 3D reconstruction, so computer graphics, computer vision algorithms into 3D information, 3D assets, so digitizing the real world and then turning them into something that can be used in immersive experiences. And so here we are looking at these experiences and the workflows and everything that belongs to that. And also in our area, AI was disruptive. So there's a change between the vintage computer vision time and now the time which is AI-based. So we can debate if what I'll show will really be AI, but at least it involves some machine learning, and it sounds cool anyway. So TRANSMIXR is also one of the projects where this work has happened, but of course there's a long tradition. You will see results from many years and various other funding sources and companies and different institutions I was affiliated with over these years, so that will be kind of a collection of many of that, right? So what are we going to talk about? It will be about 3D reconstruction, volumetric content creation, like in this example from the vintage times. So you see someone is wearing a VR headset and this person is now exploring this experience, freely looking around. In the background, you see a 3D reconstruction of Trinity College, the library of Trinity College. Inside there, you see a volumetric vologram, a hologram. Some people call it hologram. So an actor that we dressed up as a historic figure, Jonathan Swift, who impersonates basically this bus that he is there standing next to it, right? So an example of cultural heritage which combines static and dynamic elements in this VR experience. And all of this is made with classical computer vision, computer graphics algorithms. Here you see something similar, right? So now someone is moving a mouse inside the Unity game engine, but later you will see examples also people wearing headsets. Again, it's a 3D reconstructed static background. In this case, the showroom in our lab in Lucerne. But this time it is a Gaussian splat, right? So a modern way of 3D reconstruction, and the foreground volumetric video in this case is something, it's an anchor person of the Slovenian television. It's generated by an AI method, right? So before you've seen the vintage, this is both based on AI in that case. No? So let's look at first at traditional ways of reconstructing the real world, right? And If you've heard about computer vision basics a little bit, you know that if you take an image, the 3D information is lost. You cannot tell anymore where a point has been once it lands on the pixel on your image. In order to reconstruct it, to find back the 3D position, you have to take at least a second view, so you can construct something like this. So you have two rays, and where these two rays intersect in the real world, that's where the 3D position is, right? This is the basic, or one of the most basic principles of 3D reconstruction in computer vision. So you can do that then, of course, with more images and in more sophisticated ways, right? So here you see an example where someone went through the library in Trinity College, taking lots of images, and then putting them into an algorithm which basically does something like that, right? In this video, you see here, there's the camera position. So the camera intrinsic, extrinsic parameters were estimated, as we say. So the positions and the directions of the cameras. And also the 3D point cloud has been generated, right? So these are classical algorithm structure for motion, multi-view stereo, in a tool called Colmap, a decade ago, which was state of the art for these tools, and which is still quite good for that, right? So that's a reconstruction of Trinity Library. Here, the example of this detail of one of these curves. Again, you take a lot of images, you put them into the algorithm, and you get this 3D model, right? So a full 3D model, 6 degrees of freedom with full parallax, right? That can be viewed and rendered from any viewpoint. And again, you see these visualizations of the input cameras that are in there. So this is quite common and state of the art, also known as photogrammetry, if you've heard about that. So the way of taking pictures of the real world and then taking them into 3D models. You will also see that it does not always work perfectly. So there are imperfections in these approaches. For instance, if you look at what is available here, it's quite incomplete. The windows are not well covered. So there are limitations to these algorithms. So in this example, for instance, you see that we had to manually take it into a 3D tool like Blender and then to adjust it to create this 3D model that you've seen in the video before. But this is basically state of the art. And meanwhile, there are tools out there that you can download, freely available tools for your phones like Reality Scan, which you can use to create such things yourself. So 3D reconstruction of objects. Who has used something like that, 3D? So people are familiar with that. And this is an example that I really like, which shows you what you can do with it. This is Hintze Hall in the Museum of Natural History in London. And you see it's a full 3D model. So I can freely move around here. And it's a photorealistic reconstruction of this amazing building. You can also select some predefined viewpoints here and otherwise freely explore this, right? So you have a full 3D model just generated from images. Go up there to the giant sequoia and look down there. If you look into details, right? If I look here, you see there are imperfections, right? So this is not perfect still, but if you look at it at a large scale, you get really a photorealistic 3D model of the real world in this case. No? But as said, that's state of the art. You can do that yourselves, and my students all have to do that at least once in their classes. But it also can, so if you want to have something like that, it's quite an effort, right? If you read here, 3,284 photos were taken going around there, and also heavily post-production with in something like Blender, right? So it's something that you can use to do 3D content creation, and it's used in professional productions for games, for VR experiences, where you want to bring real-world things into your computer graphics applications, basically, in the end. So that's state of the art. Yeah, then let's look what happened regarding AI. And one seminal disruptive breakthrough a few years ago was something called neural radiance fields, NeRFs. Who has heard about NeRFs before? Right, so that's quite familiar. Basically, NeRFs is something that, again, takes multiple images as input. So, for instance, a short video where you would go around a scenery like that. but it does not compute a real 3D model, but it computes like a neural network. So it's a neural representation that knows how to render the output views, right? So you give it a couple of views, and then it learns how to render these output views, but can then also render any other view around there. So what you see there is not a video, it's rendered from this neural radiance fields, and it's for 3D reconstruction algorithms, a very complex scene with complex structures, these plants, these reflections down here in these glasses, so something that classical photogrammetry methods would really struggle with. Right? So when this came out a few years ago, it was really breathtaking for all of us working in the field, and created a lot of follow-up research, and basically every week a new publication about nerves. But then also something else came up called Gaussian splatting, which is in a sense similar, but it's much more computationally less complex, but is in a similar spirit. Again, you take images or a short video like these two videos that you see there that someone took with a phone walking around this font here, or walking around our campus, and you put it into this algorithm, and it will compute something like a 3D representation that is photorealistic and can then be rendered from any viewpoint, right? So now you see I can really, again, navigate inside here. It's a full 3D representation of extremely high quality, as long as you stay close to where the input images were. If you want to go out a bit, you will see that there's kind of certain characteristics and artifacts appearing that lie in the nature of this data that it is Gaussians, right? But as long as you stay somewhere around your captures, you get really photorealistic renderings of a quality that has not been seen before. And it works particularly well for like objects, or if you go around things. So if you, like in this case, where you go around this fountain and you get something which is on a level of quality that's beyond anything that we've known before, right? You can also go down there, and if you go out, you again see this structure of the surrounding. But in most cases, you want to digitize something like this fountain. So you go around, you cut away all the rest, and this is then something that you put, for instance, into your XR experience, and then as an asset, right? So this is also something that you can use yourself. So there are tools like Luma AI or PostSplat. Who has tried Luma AI or something already? Some people did. So this is something you can use for free. So the reconstruction and the visualization are more or less known from graphics and vision, let's say. A few details. So both of them are kind of not a model in that sense, but a volumetric representation. So we have information about the volume that we are reconstructing. Nerves are doing that in a kind of discrete point-wise setting, while Gaussians use not points, but think of it of Gaussian structures. So they're not bound. They have a certain extension and can have elliptical shapes. And basically, when you compute an output pixel, you are integrating along array. So you're shooting array into your volume, and you are integrating all the contributions of these Gaussians, and then you get this output. So this makes it possible then also to represent transparencies or reflective surfaces that look different if you go from different sides to sides. It also means that these Gaussians, they can degenerate. Right? So some of these artifacts that you see here, the spikiness, this is basically Gaussians with very weird shapes and long-lived things. Right? So that's what I said. It's in the nature of this data that you have these artifacts if you go very far away from your original viewpoints. Yeah, but Gaussian splatting itself is known in graphics already since 20 years or so. People have been described that. But the clue why it is now so booming is that based on this representation as these little Gaussians in space, people came up with this machine learning behind to take images and then learn this Gaussian representation. And that makes it now so popular. But the principles of splatting, of Gaussian splatting, are not new. Okay, so basically everyone can do things like this. So that was done by a journalist, a layperson from the Slovenian television who went to this location, which is in the beautiful Planica Valley in Slovenia, where there's a ski jumping arena, and took a video and turned it now into this Gaussian splat. So we can visualize it in the tool, we can walk around, but it does not yet tell us how do we make a compelling XR experience out of that, for instance. Right? And this is what was our aim in as part of the TRANSMIXR project, where together with the colleagues from the Slovenian television and the French press agency, AFP, we wanted to explore how Gaussian splatting can be used as a tool for immersive storytelling in a journalistic context, where it is most interesting, or where it is interesting. So you can, for instance, if a journalist in the field can take a capture like that, that you can immerse audiences into news stories anywhere in the world. So in war zones, in disaster areas, for instance, places where people couldn't get easily, maybe. So that was kind of the aim, to showcase this, the use for immersive storytelling. Right, so we assume that reconstruction can be done, but actually how to make the XR workflows is not yet fully developed, right? So that was then the aim, the objective in this project, to develop and showcase this in a real example. So that involves then a couple of more things to do, right? So capture, let's say, and 3D reconstruction is done by the tools like Luma or PostShot. But then you want to clean it up. You want to extract only this piece that you want. You want to maybe recolor it or do any side of other editing that you're used to from classical things that you do in Photoshop with images, or in Blender or Maya with 3D geometry. But this is not this type of data. This is kind of little Gaussians, a huge cloud of Gaussians, which can be 1 million of these Gaussians. So how to edit that is actually not well developed yet, right? So there are first tools that we use, right? So here you see, for instance, Philip editing one of these Gaussians and kind of turning it into that we want to use. But then the next step, also to integrate it into the game engines like Unity or Unreal, is also not easily resolved, right? So there are tools, plugins to load Gaussian data into them, but still you don't have something like collision, right? So if you want to walk on a surface, it doesn't work with the Gaussian structure. So you have to do something more. If you want to interact with them, if you want to do collision or something, that all doesn't exist on these clouds of data, right? So the integration and the editing is something that still had to be developed. And so here you see, for instance, Mike is working on the Unity integration of these Gaussians. So these two areas are really not mature yet. Yeah, and finally, the audience can experience the product, right? And here you see some early visualization. So me exploring a Gaussian splat, basically flying in midair and looking around in this scene. But in other places, here I'm on that stage, I can look around in the stage, and it's not 360, but you can really walk around and have full motion parallax. Again, fly around. Here I walk on the surface. So this is maybe one of the first examples of a VR visualization within a Gaussian splat. But that was obviously not yet a good enough experience for a full thing. So, but then we engineered it basically into a full experience, or VR Planica experience, where we anchored the person to fly over the resort in a hot air balloon, and you can explore different settings there, also walk into different areas. So there's a little trailer for that. So these are all renderings of Gaussian splats. There's also volumetric video appearing. So that's this anchor person of the Slovenian television welcoming you. And then you can visit these different places and be immersed in a real environment, right? You can teleport and do all of these things, which, as said, requires some additional work. So and that's something that users really liked. So you can take their miniatures, so you can take them and basically even throw them away. And there is a space where there's an interview with a climate change expert, also set on video walls. And yeah, basically that's kind of the idea. And yeah, this is just ready, released. So we showed it to first people. We ran a user study with that is currently submitted for review and also a technical paper. So hopefully soon we will, you can read all the details about this, this work. But as I said, actually the capturing is easy under certain conditions, but not always. So for instance, rooms are not so easy to capture. It has to do with the circular versus outside-facing capture, also with the size, with the overlap of the images. So a lot of influences here. So we learned from from Planica that attempts capturing inside rooms were not so successful. So in a follow-up project, we are now also looking at optimizing the processes in a way that it would give you best possible reconstructions for indoor scenes. This is again our showroom, and you see imperfections and artifacts, but I think it's quite photorealistic for what you can do to capture an indoor scene. Here is a lecture hall. Also, you see still these floaters around there, but quite a good quality. For if you want to capture a room and make a VR experience, this is the best possible way to do it currently. And this is a very small conference room, so the smaller, the more difficult it gets. But if you look, for instance, through the window, so even the transparency and that is captured quite well by this algorithm, right? And also this will hopefully be published in a couple of months. So you see really work in progress and sneak peek previews of what we are doing. Right, so far for the static part. I think I have to speed up a bit. So this gets too big for single PowerPoints. If you have too many of these videos inside. So I have 3, so we have 1/3. So then let's look now, that was all static. Let's look at how do we capture people, right? And if you think back of, you walk around and take pictures, that only works for a static scene. If the content of interest is moving, you cannot move the camera, right? So you have to use multiple cameras that are synchronized from different viewpoints. And the traditional way of doing this is having a studio like this with multiple synchronized cameras where you capture a person, for instance, and then you can do the same or similar algorithms to turn that into a 3D model for every timestamp of your sequence. And you have basically a dynamic 3D reconstruction that can be then a mesh, which you can then put into your scenery, right? So you can bring real people into XR, right? Not avatars in the sense of computer graphics people, but something that you captured. So here you see Matisse, our colleague, not today. So this is now someone holding an iPad and an AR visualization. So the background is real and this content is put in there, or in the left, it's a Snapchat filter, right? So it's computer graphics. You can put it into Snapchat. Do all sorts of funny things with that. And on the right side, you see one of the main developers, Rafa Pajes, who was at that time postdoc with us in Dublin at Trinity College. You see the nature, right? So a dynamic changing 3D object, but which is a real object. So it's not computer graphics. And here are more examples of how that can be used. Or another one. Right, so here, again, I'm wearing a VR headset. There is a room with a couple of these volumetric videos or volumetric holograms, full 6 degrees of freedom, right? So you can see the full motion parallax. There's Rafa again greeting and showcasing how that can help you to bring real people into XR. Right? Yeah, and basically what you saw in the beginning, the video here on the right side, is that's how we also generated Jonathan Swift, this person, and placed him into Trinity Library. On the left side, you see the same volumetric content, but now seen through a HoloLens. So the background is real, and again, augmented cultural heritage museum visit. There is this person appearing inside the real background view, right? So bringing real people into XR is kind of the keyword. So traditionally, there are different ways of how to reconstruct people. One is called shape from silhouette or voxel or reconstruction, where you basically you assume that the area or that you want to reconstruct is a volume, and then you can think of it like a sculpture, the block of marble, who kind of models it until you have the object of shape that you get there. But done with multiple images and segmentation and projection, but it's basically like that. In the end, you get a volume of your object of interest from these multiple shapes. So from this volume, in several steps, you can then carve out the outer surface and get a mesh, and that's when you have your 3D mesh representation, which is convenient for computer graphics to be processed. So this is also something that is in principle known since 20 years. Right? This process of a shape from silhouette. You can also do what we've seen before, just take images, match them, like the same thing that we've seen, structure from motion, multi-view stereo. You will get something like that. So that's captured from 6 cameras, 6 handheld cameras. Again, Rafa, also a cool breakdancer. You see there the colleagues standing around in front of our lab in Dublin, and you see this can be quite noisy, but it can also have quite some detail. This tends to not have detail enough, but it's quite stable. So the idea would be that you can have, let's combine the two and get the best of both worlds into, you can filter the noise a bit, but it will still be, you will have holes and different problems with this approach. The idea will be to bring those together. Another thing that we added is a first machine learning tool is by that time in 2016, 17, something like OpenPose came out. So a tool which, a machine learning tool that given an image with a person would give you a skeleton of the person with certain key points, key bones estimated, right? So at that time, it was just 2D, right? So you could do it, you could get these key points for a 2D person. But if you have multiple views, you could do it for all of these, and then again, create the 3D model out of it. So from the 2D pose estimation, generate a 3D pose. But this was used only as a helper in this hybrid system for classical multi-view reconstruction. So basically what you see here, it uses the point cloud estimation, structure from motion, and it uses the volumetric. So it combines the both worlds. The volumetric is guided by a 3D skeleton. So here the 3D skeleton is estimated, and this helps, it's just used as a helper at this point. I will show an example how it does that. So at that point, you have the dynamic point cloud, and at that point, you have the volume. And here is a data fusion that combines the two into the final output. Basically, it filters the volume towards the point cloud. I will show an example in a minute. But this basically combines the two. But before you can do any of that, you have to do some basic vision algorithms, right? So the raw images first have to be color corrected because cameras are never color aligned. In order to do something meaningful, that's a basic step. Then you have to do calibration, camera pose estimation. And things can go seriously wrong. It's always a problem also in our latest work that I will show you later. And for the silhouette reconstruction, you need to do the segmentation. right? So this is the basic computer vision. Then it goes into these more high-level reconstruction algorithms, and in the end, you get your 3D models. And for every time step of your sequences. Here you see some results. So this is what comes out of the multi-view, the shape from silhouette. And this can be quite inaccurate on a volumetric way, especially if you use only a few cameras. If you have hundreds of cameras, it will be more accurate than this. No? But our goal was also to do something which is possible to do it with an affordable camera setup. Here is the improvement that you get from using the skeleton model. Basically, an algorithm that reasons about, well, it is a human. So everything that is too far away from a human surface can be disregarded, right? So this is the final output of the volumetric branch. And here you see how we add back detail from the point cloud, right? And finally, if you put the texture back on it, it looks photorealistic, right? Like in this example, which was also captured in a 12-camera setting, right? And it's quite comparable to other things that use like 50, 60, 100 cameras, right? So not perfect, right? So you will see inaccuracies and artifacts, especially along boundaries, but quite good to create such assets that can be used in such an AR application, right? So that's why we also received a nice award for that paper back then. And here you see it used in the project. So it was, again, a cultural heritage example. So people would visit a castle in Ireland, and this is kind of an actor acting the former castle owner who was quite a bad guy. So they can meet that person inside the environment. Here again, an example rendered through Magic Leap, also AR devices, really putting, some people say, holograms into the real world view. Handheld virtual tour guide example, visit Trinity College campus grounds. And as it's 3D information, you can also put it on glasses-free 3D displays, like these looking glass displays where you can see the 3D without glasses or any headsets. Yeah, it's a 3D asset that you can take into your application, basically, right? No stand up today. Right, so we took that to a good point, and obviously this is something that there's a demand for. So basically Rafa, who you know already, and Jan and Kostas, they founded a company called Volograms. So they took these algorithms into a startup and are now marketing this volumetric content creation. But they're not, it's not a studio, but a cloud service. So people can do their captures wherever they want in their own settings and transfer the imagery to the cloud, and they will receive these assets, the 3D holograms then as a result. So that is one example, but there are many more. So that's also quite an established thing. So also a seminal work was by people out of Microsoft in 15. But you see, this is kind of a high-end studio with over 60 cameras and depth sensors and all of that, right? So the high quality end of things, but similar algorithms. So again, they compute something like a polygon soup, right? Disconnected little surface patches. Then they combine them into a complete surface. Then they make a mesh out of it, but this mesh is first not stable. So you see it's a separate mesh for every time point, which is unfortunate for any further processing. So they turn it into over a period of times, time-consistent mesh, right? You see it keeps stable for a couple of times. And then they put back the texture and get really these photorealistic reconstructions of the human as a result. That is 8i. So there are a couple of other players in the field. 8i is one in New Zealand. Also in this video, I think nicely you can see the efforts that are included in creating such content on this professional level. So it can also cost like couple of 10,000 per day to do something in such a studio, which is of course prohibitive for any sort of non-super high-level professional production. Right? But these studios, like based on the Microsoft, there's a couple of studios worldwide in London, one in Zurich, and that are run and where people can go and create such volumetric content. So that's the high end. That's another example of, out of Intel. Again, so there's no camera moving there, right? So you can do the matrix freeze effects by virtually moving the camera. Also here you see some artifacts if you look closely. But yeah, as long as you don't do such things, you get a very cool representation of the 3D scenery. And yeah, that was captured in a quite an advanced setup, right? So not the affordable setups that I mentioned earlier that we did, but this is kind of the high end of doing these things. Okay, but then AI as well hit in the dynamic area. And the seminal paper here was PyFu, pixel-aligned implicit function, which was basically a neural network that would take an image, and it had a data set of images of people and corresponding 3D models. And then they built a network that, taking an image, could create a 3D model. Right? And it was quite straightforward after all, right? So standard machine learning. And the clue was that early on they had access to a huge data set of 3D models of humans, right? And you see that that's even from a single image you can get 3D models. They're not always, they look quite nice in most cases. Even the background is generated by generative AI. But it's not always super accurate, right? So if you look at this foot, for example, right, it doesn't look too realistic for extreme viewpoints, as there's a lot of 3D shapes that explain this 2D image. So there's still some ambiguity here, right? But it also works surprisingly well on a frame-by-frame basis for dynamic scenes to generate dynamic 3D reconstructions just from monocular video. That is also something that Volograms then looked at. So they also developed a similar AI approach that could take a single video as input and then turn it into a 3D model, basically. Right? Like you see here, and then you can do everything what you can do with 3D models as well. Right? Yeah, and you just need a single video as input for that. And that's also something that is available as an app. So you can go to the App Store and download only for iPhone the Volu app and do such videos yourself. So basically, it says you don't need these high-end studios, but a single video will be sufficient for doing volumetric content yourself and to bring people into your applications. So there are the plugins are available, so you can export that content and integrate it into Unity, Unreal, and different WebXR, different platforms. All of that is available. Here are also examples of a more professional use case where we worked with the Fox News, Fox Sports, and the Irish national broadcaster, RTE. So we got some footage of sports people and turned them into such 3D models, and then basically explored how that can be used for virtual production scenarios, right? So where you can integrate these 3D models into sets and these things. Yeah, that's the example from RTE. Right, so when you have these virtual studios and AR productions, you can also integrate such forms of 3D models into these. Here another idea that we had working with a local museum of arts, basically creating an AR application where visitors to a museum could meet the artists. Right, so you get your app, you hold it up, and the art functions as a marker, and then a volumetric video of the corresponding artist is played. Right, here you see that in action. So that is the painter, and you can meet basically the person, and they can tell something about their work, in this way. So that's, for instance, a 90-year-old painter who painted this painting in '67, the Chalet Psychédélique. So that was a time of freedom and hippieism, and that's how all of these colors, and that is inspired. So you can hear a little bit of his work, and that's how we captured it. So we went there. So this also takes the production out of the studios, right? So you don't have to fly people to London or to the studio. You can do the capture in the wild with these types of settings. So here we went there just with 2 lights and an iPad, and basically could do the capture and then later integrate all of that into this app. Right? We did a small user study on that, which felt like, yeah, people really appreciated this type of application, of an AR application to enhance museum experiences and really meet or see the people who are the artists behind the work. That's also something to mention shortly. Well, one thing that is important about any of that is, if you want to think about real scenarios, is the full pipeline of transmission, right? And this data can be quite a lot of content, right? So the high detail, high accuracy reconstructions can be something like a gigabyte per minute. Right? So if you have your detailed meshes, you can get away by reducing the mesh resolution a little bit, but you still end up with something that is of really, really high bandwidth and data rate. So compression and streaming and transmission are really important, and a whole research community is looking at that, right? Not only for meshes, but also for point clouds, how to best compress and represent them. So to think about the whole pipeline, from capture to display. So if we say, okay, acquisition and processing, that's what you saw before, and the display, but compression and streaming becomes important. So how do you represent it? Is mesh the best, or maybe point cloud? Here you see different encoded versions of that content, right? So the heavier compressed, you get compression artifacts. So that's all a very active area of research, and also the quality assessment, right? Because classical quality assessment will give you 2 images, and you look at them, and then you rate them. You've heard about such things during summer school. Here, it's interactive content. It's 3-dimensional content. So you have to come up with new ways of how you present that to users and how you judge the quality. One way would be to render something like a circular view and show the video, but that's not interactive still, right? So people could just go close, or all of this, the processes of how to properly evaluate this is ongoing research. And I think we will hear from Emin later about that. And that's also work of Emin. And so all the quality assessment an own research area. So here you see, for instance, how this data looks like. Now we said we have a 3D mesh, and a classical 3D mesh has then texture associated with this. We said we want to keep the mesh consistent over at least a second or so, and here you see what you get is a texture atlas like that. So that's mapped onto the mesh. So you have a dynamically changing mesh that you need to compress, and also this video. Right? So for the video, you can use standard video coding, but you may also do things differently and better in this way. So something with a lot of opportunity. What we looked then also in the TRANSMIXR project is to integrate this into GLTF, which is emerging as the new standard for distribution of 3D data over the internet and other platforms. But it is kind of a standard very much comes from the computer graphics mindset, right? So where you think of scenes, you think of nodes, like you see in this view, and there's a mesh, it has material, right? So that's the computer graphics way of thinking. And that's true because volumetric video is computer graphics. But on the other hand, it's also video, right? So and in the video world, you think about frames, about timelines. So it's a little bit of an incompatible worlds, a little bit, the video and the graphics world in this sense. So in order to make this possible, we developed an extension to GLTF, which basically is a player that holds this volumetric content and basically updates in this GLTF file. So it puts in the mesh at every time instant, it decodes the video and puts it in as a texture, right? Because here you have every time instant a new mesh, every time instant a new texture, and then you can display and render it, right? So that's something that we developed in TRANSMIXR, also presented it at IBC last year, and also in the Centrum Motion Imaging journal, it's been published. On top of that, we also developed a streaming system, right? So just as an example, so here you have a client. So here you do all the content creation, and then you have here the server which holds then the video and the mesh, and then it basically plays it all back over existing video and video streaming infrastructure like HLS. Right? So that's all what you can then build on top of such a standardized representation. So there are more approaches in MPEG and others for standardizing these types of content. Is all emerging and not well established yet, but it shows that this is really an important part as well if we later want to do things like real-time communication. Right, so holographic communication, which many people are looking at, including ourselves, we will need streaming and compression as well. Right? So we have submitted that also to Kronos, the people who are standardized GLTF as an extension. That is the end of part 2. Okay, so we let me see. This one. I need to go to the end. Yeah, we are meeting our KPIs for the EU project. But Pablo, this show will be on the video now, so that will be funny for people watching. Anyway, so we have to do some post-production of that video. So let's continue with some things which is our current research, and literally like the last results that I got in, I received them this morning. So of course we are interested on the AI side of volumetric reconstruction. You saw what Volograms is doing, the monocular approach, but now we also want to use something like this for the high end, for the high quality reconstruction. And we went through the state of the art now in the new lab in Lucerne. Basically a literature review, what you would do, right, if you start a new research, and got a good understanding of the field. We also plan for an overview paper about that sometime soon. And in particular, we identified something which is called GPS Gaussian, right? Generalizable pixel-wise Gaussian splatting for real-time human novel view synthesis, which we are very impressed by this work, a CVPR paper from last year. And you see here a real-time processing, right? So she's captured in this setting here, and this is the real-time rendering of the person. But you see also it's quite a setting which is not on the easy side. It's probably not capable to do that in the wild in this way yet. No? But that's something that we were looking at, and because it's high quality, it enables even real-time performance. It uses fewer cameras than other methods. So recently also really super impressive things came out of Gaussian renderings, but which use like 100 cameras. So that's not something that we wanted to look at. Something that is reasonable middle ground, maybe 12 cameras, 10, 12 cameras. So that's what we would be interested in. And yeah, that is basically the reasons why we selected that. And we started that in last spring, setting up a few GoPros that we still had in the lab and doing our first captures and reconstructions with the method. And yeah, it works. And then but the goal was really to build the whole pipeline from capture, processing. So here a lot of pre-processing has to be done, like always, color matching, camera calibration, segmentation, all these low-level vision tasks still have to be resolved every time again. Then this is actually computing the Gaussians. We still plan to merge them because you get a lot of Gaussians in this case. We don't have that yet to merge them. But then also to put them really into the game engines and to render them as part of XR experiences then. So we got cameras in last fall and started our first lab setups as you do it, right? So capturing ourselves, it's kind of RGBD, so depth cameras, femto bolts, so the successors of Azure cameras, if you worked with those. And then we did what scientists typically do. We set them up and basically did our first tests. And this is Athanasios Charisoudis, the PhD, one of the main people working on that. And you see that there is a limitation here. So basically, there is a physical maximum length on these cables. So if you want to do a circular setup and just want to use one computer, it limits the radius of what you can do, which is something which turned out later to be unfortunate for what we were planning, right? But still, there's also some serious engineering happened here, basically to set up the system and to build a software that could read all of that really reliably into a single computer. That's what Thanos did, for instance. Here you see him again with a color chart in the beginning. Now, this one, so calibration always has to be done. So you go in with calibration patterns, you go in with the color charts in each camera to be able to do this low-level vision steps later. And then you do your typical scientist type of moves inside there. The most interesting part is the Greek dance, of course. And then you start processing it, and you realize, well, the depth. So we also want to use the depth map, depth capture depth, as I will show in a minute. You see that for some reasons, the depth data may not always be as good as you would need them, right? So there can be a lot of imperfections and flickering in the captured depth. So for instance, if you have a circular setting, these are the other cameras. So they are emitting IR light. So that influences the depth. Also here in the floor, you see imperfections because the floor was IR reflective, right? So we could have used a better carpet there. All learnings, no? But still we were able to do with some post-filtering, bilateral filtering, and spatial-temporal bilateral filtering to get reasonable depth maps out of these captures. And then, well, basically that's already enough. So from video and depth, you can already render virtual viewpoints, and that illustrates basically two neighboring cameras, camera 1 and camera 10, which are the neighboring ones, rendering just from the depth map and virtually moving the viewpoint. And as long as you are close in the viewport of a camera, it looks good. But if you go further away, the quality drops. But if you put the two together and switch from the one to the other, you expand your virtual view range accordingly, right? So here you see the combination of the two. And here you see each individual camera, right? So if you now add more cameras, maybe put them closer together, you can get the coverage of the space that you want to reconstruct. And then a detail of this GPS Gaussian algorithm. So GPS Gaussian basically takes pairs of cameras and it computes a depth map for the two. And it assumes kind of something which is close to a standard stereo pair of cameras. So the cameras have to be quite close and the whole arrangement has to be quite regular. Otherwise, these cameras are not fulfilling the condition to get a good depth estimation result here. In turn, they don't need depth as input. So at this point, you get the disparities, and then there is a Gaussian regressor, not even a learning. You can debate if that's even machine learning, but it turns the depth then into the Gaussians. That's what GPS Gaussian does. So it has the advantage, it doesn't need a depth as input, but it has a disadvantage on the settings of the cameras. So our idea was to to use depth from the sensors as input and not rely anymore on the depth estimation, which would relax the condition on the setting of the cameras. So we would be able to place them irregularly and place them in different ways, and then basically take the depth input and the image input and then run that through the regressor. And yeah, here you see the comparison results. So left is a point cloud rendering. In the middle is our raft-free version of the GPS, and on the right is the standard version of the GPS. The details in there, so the quality, we are not happy with that yet, but that comes to all the imperfections from this first capture. But in principle, we can show that, looking at the numbers, that the Gaussians are better than just the depth, and that our raft-free GPS is as good as the vanilla GPS. So, but we can now use arbitrary camera setups. That was the conclusion from this initial test. I will show more results in a minute. We also have the integration with the platforms ready. So here you see a dynamic Gaussian played back in Unreal. Right? So we also have it for Unity. So the platform integration is already done. It's again a very early result. So it's not about the quality here, but about the integration into the platform. And then here you see the same Gaussian now rendered in a full sample scene that comes with Unreal. And yes, we have this as a clear content, and I want to show this, right? So you can then also do relighting and interactions with the environment and these things once you have it in something like Unreal. So this part is done, and we are just a few minutes, right? So there's also some work behind that, right? So the rendering of a single Gaussian, there are plugins for that available, but not for dynamic Gaussians. So we built something like a player which would take these Gaussians frame by frame and then kind of play them back with the help of this single frame player. But we have this Unity and Unreal integration also ready. So that led us then basically to a new setup of cameras, which we just finished a few weeks ago. So we arranged them now in a half circle, as you see here, because our aim in the following is to capture performances on the stage in the wild. So we want to go to concerts, to opera, rock, to theaters, to build this up and then to capture something like a stage. So we don't necessarily need the backside, although with Gen AI and placing them on the sides, you can already get quite good information from the back. So that's kind of the setup. You see there's an IR absorbing carpet now, so we won't have problems with that. We have background, we bought lights, so all of that was properly set up. We also integrated a professional high quality camera in there and an iPad, kind of just to capture that as well and to see what we can do with that. And then we did a first round of, calibration is something that made us problems in the first run, but is now rock solid and captured. And we did some first captures. So we captured like 6 to 7 performances inside there, also including something like that. Music, also having multiple people inside there, with the goal then also to create a data set. So it will be maybe 10 to 20 videos, also have multiple people in different clothings, different genders. So we try to be diverse a little bit in that. Also maybe something like a theater play of a longer sequence of maybe 5 to 10 minutes. So this data set is currently being prepared. We will do another shooting session in a couple of weeks. And just last night and this morning, the first results came in. So this is now GPS Gaussian renderings, the first ones out of these new captures, still with the imperfections and things we want to address in the following, but the whole pipeline basically is established in the first version. Right? Yeah, and all of these. So again, in one side, you see a fixed camera view, which is not an original camera view. And in the other side, you see kind of a virtual camera moving around the object. Again, Thanos. And you see all the researchers, right? So here's Lam Kit Jung or James, martial arts, Thanos with Greek dances, Simone Croci. And yeah, I see we are quite confident that we reached a good status with that, with the state of the art in the field. And another example, now it's 2 moving cameras, right? So in the following, we are going to improve that to prepare the data set and to release it. So if you're interested in these things, it will be soon available. And yeah, then to work with partners in EU projects also to use that in productions like the one I mentioned. So there's a plan for a blues rock concert in Transylvania, for opera in Ireland, and for theater in Sardinia, in Italy, as part of the HEAT project that we are also involved in the following. Yeah, so that's it. So I still have some years to retirement. There's enough to do. And so for instance, yeah, we feel AI has really disrupted our field, and we are excited about that to contribute here. So further improvements and extensions of the core algorithms is something that many people are interested in. But then also this integration with the pipelines, with the productional workflows in particular, is something that will also provide opportunities. Things like editing and animation, like how do you segment a Gaussian cloud? How do you do semantics? How do you animate it maybe even? All of that is are nice questions to look at. Also, the comparison of vintage versus AI-based algorithms is something we are interested in. Photogrammetry versus Gaussian splatting, for instance. You saw the room captures that I showed you before. We are preparing a paper submission that will compare classical photogrammetry versus Gaussian splatting in that context of room capture. And then capture in the wild, really not relying on studios, but being able to bring your content to a theater and to capture there. For the pipeline, formats and standards will be important, right? So compression and streaming, all of these things. Yeah, the end-to-end pipelines. Yeah, then looking further, combination with generative AI and LLMs, of course, right? So because so far these volumetric holograms that we've seen are playback only, so they are not interactive in that sense. But if you can combine that in a way with large language models that could in some way be communicate with them and some Gen AI elements, you could make that type of content more interactive. Yeah, and then development and application scenarios and showcasing all that. And that's the end from me for today.
So thank you so much for giving us this amazing overview of really, really cutting edge and state-of-the-art research. I can guarantee you that such an overview is very hard to come by. So I consider myself at least and all of you to be quite lucky. And I'm also very happy that you actually took a bit more time because I've just learned that food is a bit late. So we have plenty of time for questions. And we have a very nice throw mic. So let's see how that works.
Yes. Does it work? Yes. You mentioned very briefly that you have relighting in Unreal Engine, but it seems like a difficult task for this kind of data. Could you maybe comment on that?
Yeah, not something we did, but there's a plugin that implements that. So they basically compute something like a representation out of the Gaussians that is then that you can interact with, or they are able to interact with certain data that would then implement the relighting. So some people did a very first attempt to that, but of course the whole field is open, and doing it properly and scientifically is something that would offer opportunities, absolutely. Yeah.
Okay, thanks.
Mm-hmm.
Okay. Thank you, and thank you for the presentation. I wondered if you could give us more insights about the evaluation side of these methods? Because at some point, while discussing GPS, there were some metrics that you used, such as PSNR or SSIM, which I also have been used for evaluating, for example, diffusion model outputs, which is like 2D content. And I was wondering if you think that they can still be useful quantitative metrics and/or something different, quantitative or qualitative is needed, and with this regards.
Yeah, very good point, actually. So these numbers that you have there, it is very questionable if they are appropriate for this here, right? So, but we debated long how good they are, and I should have removed them because they are not meant to be something that's a valid metric here, but something that we use internally for getting an inspiration and understanding. But we would not use that for evaluation. But it kind of, in the end, before you do a formal user study and show things to people in a way that we describe either by rendering views or putting people with headsets and then evaluating them, this is what you can do in the lab for getting things. And so, for instance, here, the first thing you can do is you look at them yourself and, wow, looks good or looks bad. And then basically the idea here was we computed some numbers by having an available view and rendering something and then comparing it to that to get a rough understanding of how they compare. And just saying, okay, this, which visually we feel like is similar in a way, also corresponds in that number. But definitely this is a whole research question, how you evaluate these things. And some of you are active in that field and know very well, I assume. Yeah. But for the other, once you have a full experience, you can do a user study, like for the Gaussian splatting, for the experience via PlanetSal, we did a formal user test with Likert scales and questions and these things. That's the other way of things. But the metrics is a very open area. Yeah.
Okay, thank you.
No, I will not solve it.
Thank you, sir.
Thank you for the nice presentation. Point cloud, mesh, Gaussian splat, what is your feeling about the future? Do you think we are going to use them, all of them, in 30 years, or do you think Gaussian splat, which is extremely trendy now, will overpower everything? So what is your feeling about it?
Yeah, good point. Well, we are also inspired by Gaussians in the moment, but it's not so clear yet. I would say we have some initial, so this, for instance, shows point clouds versus Gaussians, but it's not so clear yet in which case the Gaussians will have an advantage. We found, for instance, that sometimes the point cloud renderings look sharper, but more artifacty, more noisy, while the Gaussians are more smoother and also temporarily more stable. So there is certainly something like a low pass effect that happens here, which makes it maybe visually more appealing. But that's all something that's an open research question in the field. I feel like in theory, you can also think of it, Gaussians are an extension to point clouds, right? The fallback is point cloud, and this is just more complex. But in another, it also depends a lot on the application. So there may be some applications where you want to use a mesh. And there are also algorithms that can take a Gaussian, more like a static Gaussian cloud, and turn it into a mesh. Because maybe your target application will only, or will not be powerful enough to render the Gaussian at this point, right? So there's a lot of parameters from the application side and the settings, do you want to do real time or not, that would influence this final decision of your representation. Yeah.
Question there? Yeah.
Thank you for the talk. I still use the Volu and Luma 3D app that we experienced during Dachstuhl, so thank you for that. I was wondering, how feasible would it be for us to use this sort of technology in rendering very dynamic environments? Like I do a lot of natural hazard work, like hurricanes and wildfire and tornadoes, and for this sort of a very dynamic environment shift, when and how would it be feasible for us to build something where you can experience, like being in a real hurricane or being in the middle of a tornado?
Yeah, so this will drive these approaches to the limit, obviously, right? So I think we are just at the beginning, so we can do very scenes like a human to represent them really as a Gaussian. So doing this for such phenomena like the one you described is still somewhere down the road. But I don't think there is something theoretically making it impossible. It's a matter of complexity and effort and scale, but not a fundamental roadblock that wouldn't allow that. And also, if you think about combining it with animation, right? So animation approaches, physics animations and graphics, there's actually a good idea while speaking, right? So these animation or animations in graphics don't use this type of content. But what if you do an animation of a fire or a smoke based on Gaussians? That would be possible to combine these approaches to get into that direction.
Let's check for some final question, and if not.
So you mentioned about these low-cost production techniques and also high-cost. So what's your opinion on combining, let's say, a low-cost production with an artist who can clean up the low-cost capture versus doing a high-cost capture in the first place? So what would be the pros and cons of this approach?
Yeah, well, that's a good question about where the trade-off is. And basically, all our productions are of that kind, so low cost, and then we basically refined them. No, sorry. Thanks, Siri. Sorry. But that's something that really depends on the setting of your application, right? If in the first place you don't have the budget to go into one of these high-end places, you will fall back to doing something more affordable and then rely on the labor, to get in there. And our goal with this was also to show that there are these lower cost examples, opportunities that you can choose that go this way. But I think theoretically in post-production you can fix it all, right? So, where exactly this crossing point is depending on the actual setting of what you want to do, I would say.
So, as moderator, I have the privilege to ask a final question. First of all, I'm so happy that you actually show how AI strengthens some of these approaches, image-based, capture-based, that you have been researching for so long and that many of the people here look at. At the same time, we could also expect, especially generative AI, coming up with completely, let's say, non-image capture-based approaches, maybe not even based on actual humans. So what is for you that main driver for having real people in XR and having that capture image-based approach?
Yeah, I think that, but that's also a good question that, because you could basically do similar things by using computer-generated avatars. Or you scan a person and then you have the photorealistic thing, like you then use something like meta-humans to animate them and with motion capture. So still these approaches were so far not at the level to be as believable and relatable so that you would still recognize, unless you put a huge amount of effort in, that they are not human. While there is a claim, and I would support that claim, that if you capture someone, even if it has artifacts, but you recognize that it's a real human, you can still trust you're talking to a real human. So applications, for instance, like communication, like the holographic communication, real-time communication, may be more accepted with real captured humans where you know the person better. But this is something that actually needs to be evaluated. So you would need to have the the volumetric quality at a very high level and also the animation quality at a very high level to do a comparison like this. But at some point they may become indistinguishable, and then that's anyway no more problem. But below that, it would really depend on what you want to do and which one of the two would be the better approach for your application.
Thanks so much. Let's thank our amazing speaker again.